Guys, let's make a start. Take your seats, please. Okay, so good afternoon. We're going to make a start on our new chapter, chapter 4. Before we start, can I just ask you an honest question? How many of you, raise your hand if you did actually go through the the reading exercise? Fantastic, that's about 5%. Well done, yeah, it's good. Okay, so very impressed by your honesty and not very impressed by your, by your actions, really. Okay, so this is probably the only chapter which required you to go through some reading exercise beforehand. The reading exercise was really about phase change and some background information about pure substances. But we're really going to start making we're going to make a start on using this theme table. So I hope you all have a copy of this theme table with you today. Okay, so let me just start with the actual title. The title of the chapter is Pure Substances in brackets Vapors. Because you could actually have other... Guys, quiet. Yeah, go on. Oh, right. Sorry, this one is just so annoying. Right, okay. Yeah, thank you. Okay, so the title, you could have different pure substances, but vapor is probably the most important one that we're going to be dealing with. And we're going to see actually what the other types of pure substances. Now, let's just give an overview of what we've been doing so far. Let's go on page 4.2. So far, it's all been quite theoretical stuff. Work and heat and first law and zeroth law, everything else. But in reality, if you really want to apply these equations to the real problems, such as boilers and heat exchangers and cycles, engines, etc., you really need to use what you have here, the steam tables. So if you want to use the same, if you can't, so when you chat, just distract me. You essentially need to have access to these steam tables, because when it comes to the real problems, you can't just start doing calculations, because there are lots of numbers that you need to find. For example, as we'll see here, when it comes to pressure, temperature, specific volume, entropy, etc., this actually becomes quite handy. And the reason why, I've mentioned, for example, that I have a very practical approach. I don't want you to memorize or use stuff that you won't be able to use in the future because of, for example, Google or Internet or etc. This one actually isn't one of them. This one is one of those things that you will be using in the future, regardless of whether you can find an online version of this or a calculator online. This is something that you'll be using. And people have been using for the past 50, 60 years, and they'll be using for the next few decades at least. So it's important to understand how to use this. And why do we have to use that? So let's just make a start on giving you a background on the pure substance. So a vapor is an example of a pure substance. And for example, the type of vapors that we will cover in this unit, or the ones that are actually quite common in thermodynamics, are steam, which is naturally the vapor form of H2O. Then we have ammonia and refrigerant 12, or R12. These are quite common. These are used in a lot of different cycles, and for example, R12 is the one that you would use in a fridge, in that sort of cycle, or any sort of cooling cycle. Steam is used in a lot of, literally most of the power plants. That's how you would transfer the power from whatever the cycle is about. For example, if it's nuclear, if it's fossil fuel, whatever you're burning, or gas, still you're going to use steam in order to rotate the turbine to generate energy. We'll come back to that later. But really, these three are quite common. Now, let's start with water, because that's the most common and probably the simplest one. You all know, and obviously if you've done the exercise, reading exercise, you know the three phases: solid, liquid, and vapor. Especially pay attention to the term steam, because on a lot of, from experience, you might actually get confused about the term steam. Steam is only the vapor form of H2O. If you have R12, or if you have ammonia or other gases, for example, you can't use the term steam for those. They're just going to be vapor when they're in the sort of gas format. Of course, you don't only have to have a single phase. You could have two phases, which could exist at the same time. That's what we know. And in fact, in thermodynamics, that's the case in a lot of situations, especially when you have liquid and gas or steam coexisting at the same time. We'll come back to this. The main assumption here is that they're going to be still dealing with equilibrium. So all the assumptions I've been saying so far, still valid. You're looking at all the changes at a very slow pace. We assume that there's not going to be a significant or sudden change in the system, and therefore equilibrium applies. And what we need to do now, I just wanted to sort of describe the pure substance for a second, and I'm just going to refer to the first page of the reading exercise. On page 4.11, there's a very good figure in here, which I'd like to pay attention to this one now for a second. So, pure substances, the reason why I said the title of the chapter is Pure Substances in brackets Vapor is because you could have, for example, gases as well. And this actually sort of tells you exactly where we are and how we categorize the pure substances. We use the term vapor if you've got steam, ammonia, or R12. And if you've got some of these gases such as carbon monoxide or carbon dioxide or hydrogen, then these are the gases that we're going to have. So I want you to picture, I want to memorize this diagram and make sure you're clear on the terminology that we're going to be using. As we'll see later, vapor is the one that is a bit more challenging. The reason is because, and this is quite important, this category is the one that we use the steam tables for. So this, what you see here, is for these three, or in fact, you could have more, but these are the three most common vapors. Guess what? For these three, you actually use the type of ideal gas laws that we have, and we'll come back to those later on. But essentially, what you will use for these would be the form of PV equals MRT, and there are lots of different variations of this equation, but normally this is the sort of the ideal perfect gas laws that we will use for these gases. There's something in common between all these 6 and other more examples that are not included here, and these are the 3 features included in here. So these are essentially the 3 attributes of something. If you want to call it a pure substance, it has to satisfy these 3 criteria as a minimum. Homogeneous in composition. This means that essentially you have to have the same ratios of atoms throughout the system. You can't have varying compositions. For example, in this part of this, if it's not fully mixed or homogeneous, then it can't be a pure substance. And that's the case in the chemical aggregation as well. So it has to have the same atomic structure. If it's not in that state, and if it's sort of, for example, starts reacting, or if it starts, for example, if the molecules have different buildup, then obviously that is not homogeneous, and that's not going to be a pure substance. And thirdly, there must be no chemical changes taking place with time. So if you leave this pure substance in a vessel, whether it's concealed or not, it shouldn't react automatically with its surrounding. Obviously, there are lots of caveats that we will put on this, but as a general term, for example, if you have ammonia, it's not going to change its composition over time if you leave it in a vessel or in a container. Now, based on this assumption, for example, air isn't a pure substance because it doesn't have the same composition. It doesn't satisfy most of these criteria here. And you can see, you start appreciating now what we categorize as pure substance and what is not a pure substance. Therefore, you can't find air in here. You can't use, for example, the PBMRT equation for air, unless you make some very big assumptions, for example. And essentially, so this is what we mean by pure substance. Let's just go back to where we were. Now, this diagram looks a bit complicated, and it sort of is to understand what it really means. But it's really interesting, and it has a lot of information to digest. I want to describe a few things here, and then hopefully we can start analyzing what's going on here, because this is quite critical in understanding the behavior of a pure substance. So 3 axes. So this is certainly a 3-dimensional diagram. Pressure, volume, which is a specific volume essentially, and you've got temperature in the z direction. You could be looking at this 3-dimensional diagram from different directions, obviously. If you start looking at this from the top, and this arrow, this is what it indicates, we are now looking at this diagram from the top. So you're absolutely looking from this angle, and you're not looking at a sort of any other angle, so you're completely normal. This is the sort of behavior that you will see. This dashed line represents this dashed line here. And these lines, we'll come back to these, but these are, for example, constant pressure sort of lines, or isobars. We'll come back to this. These lines that you see, and you could have unlimited number of lines on this diagram, they represent a constant property. So in this case, as I mentioned, this is, for example, it could be constant pressure. So this is the TV diagram. A more common diagram that we've been using so far as well is a PV diagram, pressure versus the specific volume. In this diagram here, these lines could be isothermal lines, so it's constant temperature sort of lines. And again, that very important dashed line represents a separation of the regions, which I'm going to come back in a moment. You could also be looking from this side. It's not included here, but I'm going to draw something. So essentially then you're going to have pressure and temperature. And if you're looking at this diagram from this angle, what you will be seeing is something a bit more simple. And I'm just going to highlight the lines that you will potentially see. You will see this line. You will see this line here. What else can you see? You would see this line. You would see this. And this. These are the lines that you could potentially see from this angle. And if I want to represent those lines on a 2D diagram, then it sort of looks like this. This is the critical point here. The critical point. This is the triple point here. The 2 distinct points in here. And what these lines would distinguish are different phases. And what I mean is that here, I'm going to have, so if you're looking from this angle, this is going to be vapor. This is in a different color. Here you're going to have liquid in this region. Here I'm going to have solid. And beyond this line, I'm going to have the gas. So this is, from this angle, when you're looking at PT, what you see is a separation of different phases. And this is what is smart about this diagram, because it brings together solid, liquid, vapor, gas, and a combination of those as well. Now, let me just go back to, for example, the TV or the PV diagram, and I want to talk about this dashed line. because this is probably the most important feature on this diagram. What this diagram represents is the separation between, so if I look at this diagram now, this is the point which we call critical point. Anything beyond this point on the left will actually represent your liquid. And you can see here as well, anything left of this diagram, this line, will be liquid. Anything on the right-hand side of this line and beyond this critical point would be your steam. If it's water, for example, let's just talk about steam. And what is here in the middle is what they call wet vapor. And the term wet vapor might be a bit confusing, but actually when you start, because we're going to be using it a lot, so pay attention to what it means. It means that it's not just liquid and it's not just steam, it's actually a combination. So here we're going to have liquid plus steam in this underneath this diagram. Actually, the next page, you'll have more relevant figures to show you that, and I think I'll start describing those regions again, and we'll make reference to the steam table and how you would read them. Something important about the steam tables is that there's no way of literally just me teaching you how to use it. You've got to do a lot of examples, and as you'll see in this lecture, we don't have a lot of materials to cover, but we have actually a lot of examples to do. And that's the only way that you will learn how to use the steam tables. Now, let's just build, essentially following on what I was saying on the previous page and about the TV diagram and those areas. This is exactly what I was trying to draw on the previous page. So you see the separation now. This dashed line in the middle would separate, this would separate the three phases that we have. Here, for example, we could have just water. Here we would have water and steam. And here, beyond this line, you're going to have just steam, or what they call superheated vapor. As far as the table is concerned, you see the page number for each of these phases. By the way, there's something else here beyond the critical point, what we call supercritical vapor. We're not going to touch, or we're not going to really talk about supercritical in this course. It has some applications, not as much as the other phases. But for example, you might have heard of supercritical nuclear reactors. That's actually when those reactors would be using supercritical vapor in the actual design. But most of the cases that you will be dealing with, you're going to be looking at one of these three phases. Anyway, so this is for H2O. When it comes to the other vapors and other pure substances such as ammonia or R12 or mercury, then we've got different pages for those as well on the steam table. You don't have to memorize these because as soon as you do lots of examples, you understand where to go. But when you learn how to use the steam table, actually it might be nice to come back to this figure and have some sort of closure, because it gives you a nice overview of where to, how to explore this steam table. Now, let's just start opening the steam table. Let's go, for example, to pages 2 to 5. Any page would do. If you've got a copy, just open one. Open page 2, for example. Based on this diagram, pages 2 to 5 would be looking at the wet vapor. So this is where we have the mixture of the liquid and the vapor. So let's just look at what we have. We've got temperature in Celsius, we've got pressure or saturated pressure, that's subscript S. stands for saturation pressure, and it's expressed in bar. We've got the specific volume, G. We've got enthalpy, and as you remember last week when I was introducing enthalpy, I said that it's so important that actually it appears in the steam table as well. F and G. F stands for fluid, and G stands for gas. And I'm just going to describe, before we move on, we will come back to this, but it might be useful to explain the fact that this is the next page on your lectures. F would be the point on this line, and G would be any values on this line. So that's just to give you an idea, but we'll come back to this, don't worry. So F and G for enthalpy, and the same for entropy. We're not going to cover entropy until the last chapter, but again, you see how important that is, therefore it appears in there. And HFG and SFG is nothing but the difference between this value minus this value. So this minus this would give you this, this minus this would give you this, and that's just a difference because you're going to be using the difference between the F and G a lot, and therefore the table would give you the difference between the two values as well. So you've got different temperatures here. It starts from 0.01, goes up all the way to 100. And of course, the reason why it goes up to 100 is because that's at what temperature the water will boil and will become steam. So that is according to the temperature. On the next page, you actually have everything sorted by the pressure. So these two pages would really give you the same thing, but actually in different orders. It's like when you start arranging, if you've got large number of files in your folder on your desktop, and you want to, and obviously in the Windows, it asks you to arrange it by date or by the name or whatever. You start arranging them in whatever way you think is actually easier. This is the same thing. If you've got the value of temperature and you want to find, for example, the saturation pressure, you'll be using this page. If you've got the value of pressure and you want to find out the saturation temperature, then you will use this page. That's sort of essentially how this works. So these are just the values that we'll have in the steam table. And here, this is actually what is described. This is what exactly I talked about: temperature, pressure, temperature, depending on what you're after. Now, let's come back to our PV and TV diagram, and let's talk more about those lines on these diagrams. So, because probably the most challenging part of this diagram is the wet vapor, because actually it's a mix of those, a mix of liquid and steam. What these two diagrams explain, essentially, is that when you have TV, T and a specific volume, it is quite useful to have and draw constant pressure lines, and these are what we call isobars. And as I said, you can have unlimited number of isobars drawn on this diagram. A terminology, again, just remember this is called critical point. That is when these two lines, dashed lines, would meet each other. This line here, on the left of the critical point, is the saturated fluid line. Just going to write this. So, saturated fluid line. And of course, we use the subscript F on this line, as I mentioned earlier. This line, which is on the right-hand side of the critical point, is a saturated vapor line. of course we use V, subscript V to indicate that. Similarly, on the PV diagram, we will have constant temperature lines, and these are called isotherm. As the name suggests, these are constant temperature lines. That's just a fancy name of saying that. And the same applies. This is a saturated liquid fluid line. This is a saturated vapor line. Now, when it comes to, let's just think about these constant lines again. Here again, we've got the isobar. I just want to give you an example. If the pressure, let's just assume that the pressure here is at 1 bar. That's atmospheric pressure at sea level. And we know that when you have pressure equal to atmospheric pressure at the sea level, then water would boil at 100 Celsius. Therefore, that temperature here, the saturated temperature here, would be equal to 100 Celsius. If, on the other hand, if I was to draw another line, another isobar sort of line here, and if I told you, for example, that the pressure on this line is 0.7 bar, which means, for example, you are maybe at a higher altitude, maybe you're on a hill or a mountain, where the pressure, atmospheric pressure is lower. And you know what happens when you try to boil water when you're at the top of the mountain? You're not going to have, water is going to actually evaporate at a lower temperature than 100. And therefore what happens really is that this temperature here, or the saturated temperature at this line, would be 90 Celsius. Sorry, 90 degrees Celsius. And that is the temperature, saturated temperature when the pressure is 0.7 bar. How do I know that? Actually, this is given from the steam table. This is the sort of information that you will find from the steam table. And of course, I could draw 0.6, 0.5, 0.5, 0.5, whatever. And that's why I said you can draw unlimited number of lines on this diagram. Now, I think it's time to start looking at some examples and using our steam table to find the answers. So the first one, we want to find the saturated temperature for water at a pressure of 6 bar. Now, for this example, you need to go to page 4. Now, why do we have to go to page 4? First of all, because we know the pressure, and therefore I need to have the first column sorted by pressure, because that makes it a lot easier for me to find out what is the saturated temperature. So if the pressure is 6 bar, then have a look at that. So the pressure is 6 bar in here, and you can read off the saturated temperature here to be 158.8 Celsius. What does it mean? It means that if you had a, for example, a pressure cooker, where you were able to, or even a sealed container, and you have water, let's say you start pressurizing this vessel up to about 6 bar, and now you start boiling the water, or you start adding a heat. Naturally, because of 6 bar, which is a high pressure actually, the water is not going to boil at 100 Celsius. It's going to take actually longer, and it's going to take a higher temperature to boil. And that temperature is exactly 158.8 Celsius. This now shows you why in a lot of power plants and a lot of, for example, let's take nuclear reactors. In a typical UK fleet of advanced gas-cooled reactors, you're looking at about 40 bar. Why do we have to have 40 bar in a reactor? when we clearly know that having high pressure means actually it's more risky from an engineering point of view, because you've got this structural damage potentially, you've got the function of the components. But on the positive note, if you raise the pressure in the core of the reactor up to about 40 bar, that means that you're going to have steam at a much higher temperature. And you want that because the higher the temperature of the steam, the better you can actually rotate the turbines and produce energy. If you were operating your reactor at 1 bar, or room temperature, room pressure, then your water will evaporate at 100 Celsius, and that's not really good, because that doesn't have a lot of energy, or the enthalpy at that temperature is actually not much to do a lot of work on the turbine. So now you start putting together these sort of stuff that you've learned so far, and then it sort of makes sense why you would come across all these engineering novelties and innovation purely based on some of these theoretical stuff that we are covering here. Anyway, let's just look at the second example. At what pressure will water at 65 Celsius begin to vaporize? Now, here we have the temperature, which is 65, and I want to go to actually the first page number 2, which I explained initially. I said, if you have the temperature, then this is the page to go to, page number 2. So I'm looking for pressure at temperature 65. That is 65 here. And the saturated pressure is 0.2501 bar. So if you want to boil your water at 65 degrees, if for any reason you want to make sure that your water actually boils at 65, you've got to reduce the pressure. And this is an example similar to the example which I gave you being on a mountain. So, and that is exactly the sort of pressure that you would need in order for your water to boil at 65 Celsius. So that was simple. The third example is, what is the saturation temperature of R12 at pressure of 1.004 bar? So this is not water anymore. This is not H2O. So we're not dealing with these pages 2, 3, 4, etc. These are all about. If you start looking at the actual title on the booklet, you actually see that this says saturated water as steam. I'm not interested in that. Then it comes to superheated steam. Not interested in that. Again, that continues. And if you go all the way to page 14, and actually you start looking at mercury, you start looking at ammonia, and you only find R12 on page 14. The first thing that would come to your mind is, why do we have 10, 12 pages of numbers for H2O and only 1 page for R12 or ammonia or mercury? It's simply because, first of all, water and H2O is more common. It's probably the most common pure substance used in engineering and in thermodynamics. So we need to have more values on the table. Basically, that's actually one reason. There's nothing else really. And will actually make sense when it comes to interpolation. We're going to talk about interpolation in a moment. So anyway, let's just look at R12. So R12 is what we call dichloro-difluoromethane. It's a very ugly name for R12, so we adopt R12 as a better name. And what we have is, we need to look at the pressure which we've been given. That is pressure 1.004 bar. And in fact, if you look at this number here, you find the saturated pressure which is given to us in the example. And the saturated temperature, or the temperature which is which refers to this pressure, is actually minus 30. The whole logic which I said, for H2O we have the luxury of having everything sorted by temperature and everything sorted by pressure. That is not the case for R12 and ammonia and mercury and etc. and other pure substances, simply because they are not as common as I mentioned earlier, therefore, what you need to do, you need to start using the first two columns in order to find what you're after. Now, we were lucky because the pressure which we were looking for is actually on the table. And it's very easy to read off the corresponding temperature from there, which is minus 30. The first thing, as a sort of a side note, the fact that at that pressure, R12 would evaporate at minus 30 Celsius, that actually shows you something very desirable when it comes to refrigeration. And if you are wondering why we would use R12 in the fridge or freezer sort of cycle and not water, that's exactly because of that special feature of R12, which makes it perfect for refrigerants, as a refrigerant. Okay, so that's the first three examples. Let's move on to the next page. So, example 4 and 5. So now we're moving away from just temperature and pressure, because there are more important stuff that you want to get out of the steam table than just pressure and temperature. And these two examples are looking at those. Now, find the specific volume of saturated water. Now, by now you should know that this is VF, and the saturated steam, which is VG, at a pressure of 1.01325 bar. So I'm going to again go back to the H2O pages, which starts from page 2, and what I have is a pressure. So what is actually useful here is that, and one thing you would notice is that, for example, that specific pressure which is given to us, 1.01325, is something that you will find in here at the bottom of this table. So the question really is asking us, if that is a saturated pressure, then what is VG and what is VF? Now, the first thing that you would see right away is that the value of VG is 1.673. Let me just draw quickly. I want you to draw this diagram all the time. This is the critical point, and at certain, for example, here we've got certain pressure. We want to find out what are these values. And if this is, for example, PV, I want to find out what is VG and what is VF. And this point will be VG, and this is the specific volume. This is a sort of diagram that I want you to draw on a piece of paper or in your mind when it comes to problems like this, because it makes it a lot easier to understand where we are. So VG is given to us in the table, so that is fine, and that is 1.673, and of course the units for that is meter cubed per kilogram. That's the inverse of density, but you know now, you already know that. You already know the meaning of specific volume, so that is what we have. Now the question is, how do we find, and this is actually where you might think that this gets a bit tricky. What is the value of VF? Now VF, which is this value here, is not actually in the table. Well, it is actually in the table, but it's not actually here. And where can you find that? If you go to page 10, this is the last page where you still have H2O, and this actually says, it says further properties of water and steam. And if you start looking at some of the values which are given to you, these are quite different to what you would imagine, and actually quite different to what you had previously. We don't have things like enthalpy, we don't have entropy, this actually really focuses on the physical properties. These are the properties that you would normally use. For example, Cp, for example, mu, which is the viscosity. For example, K, which is the conductivity, Prandtl number. So this is a special page, really, for H2O. And that's actually where you will find the value of Vf. Why? Because Vf is a property which is relevant to the water form the liquid form of water. And therefore, you will find it on this page. Now, what is the, at what pressure do we have to find this? Now, again, going back to the value of 1.01325, which is exactly at 100 Celsius. This is the value of Vf, 0.1044. So let's just let me just put that on this. So we found that to be 0.1044. Now it sort of makes sense because it's actually quite much smaller than Vg, and this is what you expect on this diagram. Say again. Which? Let's try this one. Oh, right, yes, of course, yeah. Sorry, yeah. So this is actually 10 to the minus 2. Sorry for missing this out. Actually, this is quite important. I was going to talk about this in a moment. Because some of these values might be too low, actually too high, you have to pay attention to the units at the top of the column. The reason why actually I was going to come back to the value of this is because this Vf, guess what? We know that the density for water is 1000, right? And that is the sort of the common value of rho that we would use for water at room temperature. If I divide that, if I say 1 over 1000, that obviously is that, and that would give me the specific volume of water. And the value which you found here is actually not far from this. So essentially this means that the Vf is actually the inverse of the density of your water. Now the reason why it's actually different slightly is because it is, this is the actually exact value of the density of water at the atmospheric pressure when you're at sea level. But we normally, in simple calculations, we just use 1000, but it really is 1044. And if you think about what you would have in this table, this is actually important because if you start looking at the effects of temperature on Vf, it's actually quite tiny. I mean, you start looking at 0.1 minus times 10 to the minus 2, and it goes and increases to about, let's say, 0.14 after raising the temperature from 0 to about 300 Celsius. So Vf really isn't as important, or because the variation in Vf isn't as important, you could actually get away from using a constant value of Vf in most of the situations. And we'll come back, when it comes to the tutorial questions, you'll actually see that the Vf isn't really an issue. And sometimes you've got to spend a lot of time in doing interpolations and everything else to find the value of Vf. Whereas if you look at Vg, for example, going back to Vg on page 2, look at the variation of Vg. It's actually it actually varies significantly when you move from 0 to about 100. And that is important for you to do and find the value of Vg very accurately. Now, the next topic I'm going to talk about is not really interpolation, but because the reason why we want to do interpolation is actually that is this example 5 is a good example why you would even need to bother with doing an interpolation. So the last example here is find the specific volumes of ammonia in the saturated liquid and vapor states at 28 Celsius. What is the saturation pressure? Now, again, because we're now dealing with ammonia, we've got to go to page 13. If you go to page 13, that's where we have ammonia. And the value of the pressure, so the temperature which we want to find is actually 28. And at that temperature, you can see the value of Vg. 28 here, this is the value of Vg. And the value of the saturated pressure is 10.99. That's also easy. But we also have to find Vf as well. And this is similar to the previous example. We want both the Vg and Vf. Now we found Vg. Now in order to find Vf, it's a sort of a similar story. We've got to move to a different page where we will find the further properties for ammonia. And that is actually on page 23. On this page, you'll see not only ammonia, but actually most of the other pure substances that are less common, and you'll see the physical properties which we talked about, Cp, rho, viscosity, and conductivity, for example. And pay attention to the conversion factor, 10 to the minus 6. So looking at ammonia and looking at the temperature which we want to find, something to notice is that temperature here is given in Kelvin. Now, 28 Celsius is 301 Kelvin. Now, the closest here is read 300. So I can read off from 300 and find what is the density. That's 600. And I know that Vf is the inverse of the density. Therefore, 1 divided by 600, that would be your Vf for ammonia. And essentially, it's a good approximation, really. So 1 divided by 600, that is what is the value of Vf. Now, if you really want to be accurate, though, the actual temperature was 28 Celsius, which is 301 Kelvin. And 301 Kelvin isn't given in that table. And that is a problem. Because when you assume that this is actually, I'm just going to take 300, you're making an assumption that you're not going to be 100% accurate, you're just going to go with some sort of approximation. Albeit a very small assumption in this case. This is when we would need to do something called interpolation. Raise your hand if you've ever used interpolation in the past. Okay, most of you, so this is good because you're going to be doing a lot of interpolation in this unit. Why do we have to do interpolation? Well, if I have two values on the table and I want to find something in between, that's when you would use actually interpolation. I'm just going to go through this relatively quickly because I'm conscious of time and I know you've done interpolation, so just going to be a simple example here. We're going to be using something called similar triangles. That is what we would be using in our interpolation. Essentially what we're saying is that this triangle would be similar to this triangle. And based on that, we do the interpolation. Now, based on in this sort of similar triangle sort of rule, we know that this minus this divided by this minus this would be equal to y2 minus y1 divided by x2 minus x1. That's what really this equation means. It's just sort of ratios of the length. I could rearrange this. I could swap these two. I can do that, and just that then would give me y on the left-hand side and x on the right-hand side. And let's just assume that I'm after ya. Let's assume that this is what I want to find. I've got the other 5 values, and the only thing which is missing is ya. The simple rearrangement, or this formula, which is the linear interpolation, is something which we would use in our interpolations. Let's do one simple example. Find the saturated temperature of water at a pressure of 11.5 bar. So I've got pressure, I've got water. I need to go to page 4. When everything is sorted by pressure. Now the pressure which we have is 11.5, but look at this. We've got for 11 and we've got for 12. We don't have anything for 11.5. And of course this is, you can't have every single value on the table. You're just given sort of the normal, the common values or certain increments. In this case is the values are given by the increments of 1 bar, or here less than that, 0.1 bar. And if the value that you're after isn't in the table, you've got to do interpolation. So I've got 11.5, which is between 11 and 12, and I know that will be between 184.1 and 188. Right? That makes sense. And I want to do linear interpolation between the two. Now, if you're smart, you realize that this is just really the average if you want. 11.5 is the average of 11 and 12, and I can take the average and find out what is the temperature which I want. But I want to do this using the long similar triangle sort of rule. Let me just draw something here for you to make sense. So x1, xa, x2, y1, ya, y2. In this case, x1 is 11, xa is 11.5, x2 is 12. y1 would be the second column, would be 184.1, and y2 is going to be 188, and this is what I'm after. As I said, this is really simple because it's just the value between the two using linear interpolation. But in reality, this could be a lot more complicated, and if that's the case, that equation here, or that formula, on the left-hand side, and this on the right-hand side would actually tell you exactly what you need. So this is the y side, and this is the x side. And you will end up with the value of temperature which you need to find, in this case, between the two. So that is how you would do